Hello, hello. This is Daniel Warfield from Ragmasters. I'm the only one here right now. Neil is on vacation. Also, I'm actually not Daniel Warfield. I am the prince from The Princess Bride. I've kidnapped Daniel Warfield, and now I'm the host of Ragmasters. I got a haircut. And today, I want to talk about something we've already talked about. We already talked about multimodal RAG, but we did it from kind of a high level. I talked about some sort of general paradigms and general approaches. And today I wanted to zoom in on a specific example of RAG, of multimodal RAG. And actually that example will be our technology. It'll be EyeLevel. Now, Neil and I have talked about this a lot. We don't want this to be the EyeLevel show, but I'm not allergic to our technology and I happen to know it pretty well. So I thought it would be a good sort of exercise to go through our technology, describe some of the thoughts that we've sort of had around multimodal RAG so that, you might be able to learn from that and then apply those to your technology. So this is what we're doing. How do we do multimodal RAG? And really just as a lens of exploring multimodal RAG in general. So I've talked about this before. We do multimodal RAG via a process called modality grounding, right? So you might have a bunch of text and images and maybe even video and audio, whatever. Our approach is we pass the non-textual data through that modality to text models. So image to text models, audio to text models. We don't actually do audio, but this would be an example of modality grounding. So you pass all of your data and all your modalities through a model that turns it into text somehow. And then you can do your traditional, if you want, embedding of that data. So it's all text. So you just kind of, turn it all into vectors with a text to vector embedding model. Then you can search the vector space of that text, retrieve information, augmentation generation, your classic RAG pipeline. This is like the prototypical, fundamental, highest level modality grounding style of RAG. We do this, but we do it with documents. So like our whole MO is like you have complicated documents and we want to make it exposable to a language model consistently. So we're not dealing with audio. We're not dealing with video. We're dealing with like text and we're dealing with images, but really only the images that come up in documents like these. We're not just academic documents. We also focus on like business documents, legal documents, medical documents, things of that nature. So while we are constrained, it still is pretty broad. So like, here's an example. So, we're turning text and we're actually, more specifically, we're turning a page of a document into a block of text. Now, this might seem kind of easy, right? So you have a giant block of text and you have to turn it into a block of text. Certainly you can just, take the data out, but there's actually like all sorts of like quirks to this system. Like, first of all, you might not actually have like text, like it might be a scan of a PDF, in which case you don't actually have textual data. You're actually turning an image into text. So you might need to use like OCR or something. Also, this block of text in this page is not just a block of text, right? There's section headers, there's formatting things, there's two columns. So if you just read this from left to right, top to bottom, it wouldn't make any sense because you'd read from one column to the next column, then one column to the next column. So you need to extract this data and turn it into actual text, not what we as humans perceive as text, but it's actually a combination of text, positional information, bold, formatting, etc. We need to turn this complicated thing into actual text. So that's one of the things we do. We have a parsing tool that I'll get into how it works called X-ray. But it's not just perceived text. It's also, we literally have images as well. So documents frequently have these images. So you need to somehow, if you're doing RAG, make that searchable in some way because we're dealing with documents and not just like random images. We've actually found that modality grounding is usually a really, really good strategy. So, you can represent a lot of the figures. Maybe it's like a graph, like a chart. Maybe it's a diagram. You can often represent these in JSON, which is a textual representation, but it allows you to encode things like relationships and hierarchy. So this modality grounding aspect, you could just pass it through a language model and say, hey, describe this thing. But it can get a little more advanced than that. And I think that's really where our technology sort of hinges. Like it's the most, I think, fundamental aspect. How do we turn all this complicated stuff into text that is actually useful and understandable by an LLM? So the first step that we do is we use a computer vision model. So we literally turn all the pages in our PDF, for instance, into images. So they're image data. And then we look at them with a computer vision model, and then we find all of the stuff, right? So there's a table in the bottom right. We've identified a table. We know where the title is, and we know certain paragraphs. And we also classify this data. So we don't just localize. We say this is a table, this is a figure, this is a paragraph, et cetera, right? And what's kind of cool about this strategy is we're not just like throwing it at a parser. Like it's a certainly fine strategy for a lot of applications to use a pre-built parser to just, do stuff. But the thing is, there's no perfect system. And even if you spend a lot of time building a parser, or even if you spend a lot of time learning about a parser, you really need these systems to be updatable, right? So essentially behind the scenes, we have this computer vision model, and then we have sort of two aspects of human in the loop to sort of make our extraction of this data more robust. So first of all, like we can like see the squares that get highlighted, and we can see what they're classified as. And for like certain clients that really need really high quality extraction, we can comb through manually and be like, oh, this one's wrong, and we can like move it and stuff like that, right? And that's usually not necessary, but for complex documents or in applications where everything has to be perfect, it can be a really useful strategy in having an ability to inject a human in the loop to sort of add additional robustness to the parsing system. Also, once we do that, we've now created a data set, so we can now fine tune that model to be better at those types of documents, for instance. So I think a lot of people don't think of the parser and the optimization of the parser as an important part of multimodal RAG. But when you're dealing with documents, it's like the most fundamental part, probably. And it's really, really important to do it correctly, to be able to identify stuff on a page. So we've identified stuff on the page somehow. So the first thing we do is we just like get the data out. We just get text out. And keep in mind, these are images. So what we do is OCR. So we use pre-made OCR systems, optical character recognition for looking and extracting textual information. You could also sort of scrub through the PDF itself, though it can actually be kind of difficult to align PDF elements visually consistently. Sometimes it's certainly possible. That's kind of the whole point of the PDF sort of file type, but it's like not a trivial problem either. And OCR is very advanced, and we already have images. So we use OCR and we extract a textual representation of all of the stuff. And then this is where things kind of get fun, right? So we have a textual representation of everything, but we also have like images of some things, right? So we have textual representations of the paragraphs. That's that top block. We also have images of things like tables, and we have images of things like figures. So what we've kind of decided to do is we use a multimodal LLM, not to just say, hey, what's in here, but we extract, we ask the LLM to fill out some key information. So we ask, hey, what are the keywords? Like, what are some important things that describe this figure? Can you summarize this? Can you give me like a textual description of all of like the high level important stuff? Can you classify this? So is this a table, or is it a figure? Is it a medical document? Is it a legal document? Is it an engineering document? And we can kind of manipulate based on these classifications. And we can also say like, hey, are there any things that seem like they're related to other things? So can you find things that would be important in building relationships within these elements? So we don't just tell an LLM, hey, I want you to write this as text. What we do is we extract key and targeted information. Then what we do is we know that key targeted information. And for small figures and like specific tables and stuff like that, generally multimodal LLMs are pretty good at finding things like, this is the the title of the column. Like this is the column name, this is the column name, this is the column name. The rows are formatted this way. The multimodal LLMs in the last step are really good at extracting that information. So now we know that information. We have the textual extraction from a table, for instance. And we also know the names of the columns in the tables. We know a general understanding of what the table consists of. We have some kind of, I guess you could say, metadata around the table, as well as the raw extracted textual representation itself. So we can use both those things together. And then what we can do is we can build a template. So we don't just say, hey, rewrite the thing yet. So you could, but we've found that building a template first. So saying, okay, this is, this is the important stuff, and this is all the raw text. How should you represent this data? So you ask an LLM, how should you represent the data? Not to re-represent the data. You ask it, how should you re-represent the data? And then it gives you a template, right? And we use a variety of parsing strategies and prompting strategies that we've refined over God knows how many clients to basically build a high quality template or high quality prompt that results in high quality templates that generally works for a large variety of applications, right? So now we have a whole lot of stuff. We have the raw textual extraction, we have a template, and we have a bunch of metadata. Also, I didn't mention this, but we also do section level summarization, document level summarization. We sort of try to find objects that exist in the document that should be collected together. We've basically built a whole cocktail of information that exists outside of just the raw textual extraction. And then we can finally tell the language model, all right, fill out the template. So we know the raw text, we know summarizations and all this stuff. Then the language model fills out the template. And what we have at that point is what we call a semantic object. So it's not a chunk in the traditional RAG sense. It contains information from documents, like sections of documents, but it's really, it also contains information about the entire document and information about sections and information about specific things. So it's kind of like a chunk, but it has information throughout the entire document at this point. And the whole point is that it represents an idea within a document, but it is fully contextually represented. So it's like understandable implicitly by itself by a language model. And this is an example. I didn't go into the specifics. If you go on EyeLevel.ai, you can run the X-ray demo yourself. So you can put documents in and like see what semantic objects you get out. But what I wanted to highlight is we represent the data in multiple ways, depending on the item that we're representing. So if we have a table or a figure, we found that a JSON representation is often really, really useful. So it's a textual representation, but it allows you to encode things like structure and relationships, which figures and tables often have, basically always have. So having a JSON representation for figures and tables is good. We don't construct a JSON representation for paragraph data. We always, I believe, construct a narrative. So if you give a language model a table as JSON, it can probably understand what's going on, but it's also useful to tell a table, hey, or to tell the language model, hey, this is a table and it's from this document. And this document is about this. And before the table, we talked about this. And also there's a caption below the table that says this. So having like a narrative on top of just the JSON is really useful in contextualizing the data so that when you pass it to a language model for generation, it actually knows what the heck you're talking about. And we also have the extracted text. We have the file summary. We have file keywords. We have, and also in longer documents, we might have section summaries. So we have all this data. And then what we construct is the suggested text. So we take all this data and we combine it together into a block of text that you can just like give to a language model. So it has the JSON, it has narrative, it has sometimes extracted text, I believe. It has keywords and summaries. It has all of this rich information. And at this point, I would say we have grounded our modality. So it's not just like pass it to a multimodal model somewhere and ask it to describe it. Like we do a bunch of stuff to construct a structured object that represents the data in a variety of ways that are all useful in a variety of circumstances. And that's what our parsing tool does, X-ray. I guess if you're building this yourself, you'd probably want to start with a computer vision model. You'd probably want to fine tune it. I think there are document understanding models that exist on like Hugging Face, or you can just use ours. I don't know, to be honest, that another out of the box solution exists that does it this way. There's unstructured, which is very popular, and I think sometimes unstructured uses some computer vision models. I know that there's Llama Parse. I haven't personally played with it, but I've heard some fairly good things about it. So you can feel free to experiment with those. That's our parsing tool. So you might think, okay, so we have these semantic objects, they're text. You pass it through an embedder, you put it in a vector space, you do vector search, blah, 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 et cetera, et cetera. Actually, we don't do vector embedding or search, which is really weird now in 2024. When we were building our technology, so X-Ray is the parser and GroundX is the search engine. When we were building it, vector search didn't really exist. And we played around with it, right? So we spent a bunch of time and did a bunch of work to build a textual search engine on top of these semantic objects. And then vector-based search started becoming a useful thing that a lot of people were doing. And we were like, oh, we should like do that instead, or at least give it a shot. And we didn't see a significant improvement in results. And this is backed up by some modern literature. While vector search is a fine strategy in a lot of applications, it's not like God. Like there's a lot of other search strategies. And we use kind of more classic textual search. And the reason we can get away with that is because we have these rich semantic objects that are like designed to be highly searchable, like the way they're constructed. And yes, like we have in the pipeline, and we are currently working on things on top of this sort of simpler traditional text search-based strategy. But I think all of us in EyeLevel are actually really happy we started with text search, kind of like the simpler mode of text search, because it's easier. Like it's easier to understand. Like we're an engineering company. We do data science. I'm a data scientist, but really what we're interested in is making a system that actually works for products. And one of the things I think you have to consider when you're building a system that works for actual products is how easy is it to iterate? Like, can you find issues and can you improve the system based off those issues? And can you create a cycle that's nice and tight? And the issue with vectors is no one knows what's going on. You train some vector search system, or actually you probably don't. You probably use OpenAI's like ADA embedding or some other embedding model that's been pre-trained by a massive company and you never saw the data. And then you just hope to God that those vectors that work, so that embedding puts your data in vectors that are in good spots that you can do search against. And like it's kind of remarkable that it works so well. But the fact of the matter is like you're leaving a lot of it to chance. And you're leaving a lot of it to let's just hope that this was dealt with. But when you spend all this time to construct these highly searchable textual objects, then you can just search them with traditional programmatic methods that you can then falsify and modify at will depending on specific applications. So this is, it's kind of a heretical idea, like, hey, you don't need vectors. And I'm not even saying that, because vectors are incredibly useful in a variety of applications. But we've found that it's really only minimally effective or a minimal improvement, if any. And it's significantly harder to develop on and iterate on and improve. And really the reason we can get around that is because we do this modality grounding across all of the data. And it's like these highly contextualized textual objects. So anyway, I hope you learned something. This is kind of fun. I'm excited to have a guest next week, I believe. And also, if anyone out there is interested in talking with us, maybe you think my idea of vectors is stupid and you would like to correct me, or maybe you have a cool company and you'd love to talk about it. We love to have people on. I would love if you contacted us. There should be some, I think, information down in the description. Anyway, my name is Daniel Warfield. This was Ragmasters, and it's always a pleasure.